Alright, so it's going to be section 4.3 about finding intervals, local max and mins, and intervals of concavity and inflection points. Um, First thing I'm gonna explain is when you have a unit circle like this over here, you can think of these as ordered pairs x and y, where x is equal to cosine and y is equal to sine. And another way to interpret that is like, so this one particularly right here, that's 30 degrees or pi over 6. So cosine of pi over 6 is equal to the x coordinate of this ordered pair is root 3 over 2. And then sine of pi over 6 would be equal to the y coordinate of that ordered pair, it's 1/2. And that can help when you're looking at overall functions where you can quickly kind of, like, if you have the access to the unit circle, you can quickly look at not only like the values of sine and cosine, like, but also just like you could think of it as like this is a table of x and y values for cosine and sine functions. So you could quickly, if you wanted to look at the cosine function changing over the interval of say like 0, and then like all the way around the circle back to 2 pi, then you could just look at your x coordinates of the these little ordered pairs. You could look at the x coordinates all the way around, and then you can see like they repeat, and then this section your x coordinates are negative, and this section as well, and then the other half of the circle the x coordinates are positive. And then for the sine function, y coordinates are all positive here, and then down below the bottom half of the circle they're all negative. So if you wanted to look at the cosine function changing between 0 and 2 pi, you just look at the x coordinates, and they reflect through every quarter of the circle, but on this side those are all negative, and then this side of the circle they're all positive. Anyway, we might look at that again in a little bit, but we're gonna focus on question 13 and 14 over here. So let's get started with that. 13 says you're given the function sine x plus cosine x with an interval of 0 to 2 pi. And part A is asking you to find the intervals which f is increasing or decreasing. Alright, so one way to think about that question wants to know where f is increasing or decreasing. So it's basically asking for the slope, like when is the slope positive, when is it negative. And easy way to do that is take the first derivative. When is that positive? That'll be your increasing. And when the first derivative is negative, that'll be your decreasing. So let's go ahead and find that first derivative of the given function. cosine x, derivative of sine is cosine, and derivative of cosine is negative sine. So that will be your first derivative. And again, you're looking for when is it positive, when is it negative. So we are going to set it equal to 0 and solve. So first thing you could do is add that sign to both sides, so it's positive. And if it helps, you can think of this as like both sides is multiplied by 1. They're both multiplied by 1 if it helps you think about this step. Because you wouldn't just be like subtracting it again. You would divide both sides by sine x, and you'd be left with cosine x over sine x equal to 1. That's why I put the 1's in, so you can see that. And then cosine x over sine x is equal to tangent x. So tangent x is equal to 1. One way to do that. One way to solve this is to take the tangent inverse of both sides. So if you were like doing an exam or something, you'd be like, okay, tangent inverse of 1, and then this simplifies to the tangent and the tangent inverse cancel. You're left with x equals to tangent inverse of 1. And throwing that into the calculator, you'd be given pi over 4 most likely. But then since the unit circle reflects, it would also be like, well, here your interval is only 0 to 2 pi, but it would be plus pi over 4 plus n, where n is just any integer multiplied by pi. So like you could add 2 pi or 3 pi or just pi, 5 pi, whatever you want. But any of those is going to give you back that same reference angle, which will give you a value of pi over 4 for the tangent inverse, or 1, or just basically that's your tangent x equals 1. So since your interval here is only 0 to 2 pi, then you'll have pi over 4. And then if you add pi, you would also have 5 pi over 4. So adding pi would be like adding 4 pi over 4. That's adding pi to your pi over 4. You get 5 pi over 4. But then if you added another interval of pi, like it's with this adding n to your pi over 4, if you added 2 pi, that'd be like adding 8 pi over 4 or 8 pi over 4 to your pi over 4. Jeez, hold on, handwriting's bad. It's like adding 8 pi over 4 to your pi over 4, and you'll get 9 pi over 4, which is greater than 2 pi, so it's out of your interval. So here you're only concerned with these two values. And if you want to see I guess visually without the algebra trig part of like calculating that, where you're just taking the tangent inverse, if you look at the unit circle, so tangent is cosine over sine. No, tangent is equal to sine over cosine, because it's y over x. Sine is y, cosine's x. So if you look at your x and y coordinates again on the unit circle, in our problem, it was tangent of x equal to 1. So where would your sine and cosine y over x coordinates equal 1? That would be where they're the same right here at pi over 4. Because if you threw in your x, y coordinates into your definition for tangent, then you'd have sine x over cosine x, or y over x, which would just be root 2 over 2 over root 2 over 2, which is 1. And then since the since it reflects, you would also have it in the quadrant where your x and y coordinates are both negative, your 5 pi over 4, which is down here. It's the same thing but negative, and the negatives will cancel, also give you 1. And then you can see like over here and over here it'd be negative 1. So those are not part of the solutions. But the pi over 4 up here and 5 pi over 4 down here, those are your solution points for this. So working with that, those points that solve this when it's equal to 0 is going to be like points where your function is changing from increasing to decreasing. That's what you solve for. So let me just find a different color. So pi over 4 and 5 pi over 4 are your points of interest here. And yeah, increasing, decreasing. So what was our function? This was our derivative function. So you're gonna want to find where it's increasing and decreasing by plugging in those values. And plugging in these values directly is gonna give you 0. So what you're gonna want to do is plug in values, like, so these are your x values in your equation. You're gonna want to plug in x values for like something below pi over 4, something in the middle of pi over 4 and 5 pi over 4, and then something that is greater than 5 pi over 4. So we'll just go ahead and do that. And our derivative function is, what is it, cosine x minus sine x? Pretty sure. We'll double check that. Yeah. So we'll say like something smaller than pi over 4. We'll say pi over 6. That's smaller. F derivative at pi over 6, cosine of pi over 6 minus sine of pi over 6, and see what that equals. And you can plug that into your calculator. That's fine. Make sure it's in radians if you do, because you're using the ones with pi. It's not in degrees, it's radians. And then but if you have the unit circle, you just go look, okay, pi over 6, x value root 3 over 2, y value 1 over 2. So sine is 1/2, that's your y, and cosine comes out to root 3 over 2. So going back, if it would load, then you have root 3 over 2 minus 1/2, and see what that equals. Square root of 3 is going to be greater than 1, so this is going to come out positive. So between 0 and pi over 4, your function is going to be f of x. Your original function is going to be increasing. That's what that means. and then the first point of interest, pi over 4, we'll take something between that and 5 pi over 4, so that's anything between pi over 4 and basically like a little over pi. So we'll go ahead and we'll pick something nice. We'll pick pi. It's a good value. So derivative with x equal to pi equals just cosine of pi minus sine of pi. And you could look at the unit circle, throw it into your calculator, but I already know like pi, if you have a x and y, pi is the one over here. And you think of it like a coordinate system. So your x coordinate, your cosine, is -1 at that point, because it's a unit circle, so it's unitized in a way that makes numbers nice, like the radius is equal to 1 and things like that. It's like very basic, very intentional. So that'd be -1 minus the sine of pi, your y coordinate at pi. If you look at it like a coordinate system, that's y equal to 0. So it's -1. So it's negative. And that implies that between pi over 4, did I put, yeah, maybe not inequality, or not all equal, but like between those points, I should say, is probably the way to put it. Anyway, so that's between pi over 4 and 5 pi over 4 is going to be, your x will be negative, which implies your function is decreasing on that interval. And then lastly, you're going to want to check values greater than 5 pi over 4 but smaller than 2 pi. If I could think real quick, I guess 3 pi over 2 is a pretty good choice. Least amount of thinking here. That's a good choice. That is in between your 5 pi over 4 and 2 pi. So then it's cosine of 3 pi over 2 minus sine of 3 pi over 2. And then, thinking of it like a coordinate system again, this reference point is going to be down here on your negative y-axis. So cosine, your x-coordinate, that's going to be 0. Sine is your y-coordinate, is going to be -1, but you're subtracting here, so it's minus -1. So that's +1. And then that will imply that your f of x is increasing on the interval 5 pi over 4, between x is between 5 pi over 4 and 2 pi. That's what that implies. Okay, so that is your part A. That's your part A. And now it wants you to find the local max and minimum values of f. So reusing part of our solution from part A, where we had our points of interest, critical points, I guess I should call them, is the terminology they use. Our critical points we found when we solved were pi over 4 and 5 pi over 4. But then also, critical points that we found from part A, that was just points where your first derivative is equal to 0. Those are called your critical points of interest. Those were what we found, and then our interval was from 0 to 2 pi. That's like our given interval. Was it including 0 and 2 pi? Let's see. That's because that makes a lot of difference. Yes, it is including 0 and 2 pi. So when it's including your endpoints, then you're going to want to add those to your list of critical points. So we're going to test 0 and 2 pi also, because the interval includes those. And your like whether it's absolute local max or absolute max or mins or local max or mins, if your interval includes the endpoints, you're gonna want to test the endpoints here to find maximum minimum values. And but that you're not plugging into the derivative. You're not plugging into the first derivative. You're gonna plug that into your you're gonna want to plug that into your original function right here. F of x equals sine x plus cosine x. So let's go ahead and do that real quick. Okay, it'd be nice if it was a little bigger. Thanks. Get rid of the interval. We have it written up there. So I need pen. So at 5 pi over 4 sine x plus cosine x. So we'll go back to our unit circle real quick because I don't have a calculator out. 5 pi over 4. Again, think of x and y, where x is cosine, y is sine, and they're both just negative root 2 over 2. So you throw them into your calculator or look at the unit circle real quick, throw them straight in. And that would just be 2 of those terms. So equals negative 2 of them times root 2 over 2. And then those 2's cancel. So you're just left with negative square root 2. And then you'll just plug in the other values and compare. So f of pi over 4. That's on the, if you look at the unit circle, plug it in, it's going to be the same as these, but your x and y coordinates, your sine and cosine on the unit circle, they're both positive, not negative. So that's just root 2 over 2 plus root 2 over 2 sine x plus cosine x at pi over 4 is equal to that. And that's going to follow the same logic as up here, but so that's just going to be positive root 2. And those were our points of interest. Now we're going to test the endpoints, make sure that we're not missing anything. So f of 0, sine of x, that's going to be 0. Well, sine of 0 is going to be 0, plus cosine of x, cosine of 0 is 1, so you're just left with 1 there. And then the original function evaluated at 2 pi, sine of 2 pi, same thing, 0. It's just at your coordinate system, that's the point right there, starting, end point, whatever. 0 and 2 pi, same point. So then cosine's also just going to be 1 again. So your endpoints here, they're both equal to 1, so you could rule those out because they're not local max or minimum values, really. I mean, let me be careful when I say that, because cosine and sine are wave functions, so like technically, like relative to the rest of the wave, I guess these are technically like local maximum values. They're technically local maximums, but yeah, I guess they're technically local maximums, but I feel like since it's one like between 0 and 2 pi, it's not really like, it's not really a local max because the from 0 to 2 pi isn't that far. So, and then, you're, well, whatever. Call them local maximums because it is a wave function, and cosine and sine are wave functions, and they, go back and forth, and those values of 1 are technically local max because it's going to go dip and then up and then dip. So those would be local max. But then you're also going to have, let's see, um at 5 pi over 4 you have negative root 2, which it'd be like something down here on your function. And so that would be a local minimum at 5 pi over 4 with a y value of negative root 2. Let's in your original f function, f of 5 pi, like f of 5 pi over 4 equals negative root 2. So that'll be your local minimum. If it was asking for absolute absolute maximums and minimums, then it would also be your absolute min. That is smaller than well, these are both positive ones, so yeah, that'd easily be your local minimum. But then like local maximums, f of pi over 4, you have square root of 2, which is a little bit bigger than 1. So like f of pi over 4 would be like an absolute max on your interval, but it would also be a local max. And that'd look like, you have something and then it's at root 2. So you would say like local max at f of, what was it, pi over 4? And then like if you wanted to write it as a ordered pair, it'd be pi over 4 root 2. Okay, let's quickly look at part C, and then we'll move on to the next question. Part C says, find the intervals of concavity and the inflection points. Find the intervals of concavity and the inflection points. Okay, so where's our first derivative at? Here's our first derivative. I'm going to move that down here. And then I'm also going to move this up here that I wrote earlier. I don't know if the whole thing copied, but it's okay. Make that a little bigger. Zoom in a bit. Okay, so if something's concave up, that just means you're going to take your second derivative test. And if your second derivative is greater than 0, then it's concave up. And if it's less than 0, it's concave down, which makes sense. And then when your second derivative equals 0, I'm pretty sure, that is your inflection points. It's neither concave up or down. That's the point where it's changing concavity. So, second derivative of this function here, derivative of cosine is negative sine, derivative of sine is cosine, and you're gonna go ahead and set that equal to 0. So, first thing you're gonna want to do, or that I would want to do, I would probably divide out both sides by -1, just to get rid of the negative sign so that you don't have to think too hard. That's legal, that's allowed. So it's basically like the same thing almost. Anyway, so you're looking for when is that greater than 0, when is that less than 0. So same thing as before. Choose one to move to the other side. So I'm just gonna subtract cosine x from both sides, and then again, this is like, imagine there's a -1 times your cosine x. So then just divide both sides by cosine x again, and you'll have sine x over cosine x is equal to -1. All right, that's sine x over cosine x. That's equal to tangent x equal to -1. And again, you could do tangent inverse of tangent x is equal to tangent inverse of -1, and you'll get x equals tangent inverse of -1. Or you could just look at the unit circle and be like, okay, where's tangent x equal to -1? That's where's my sine over cosine, my y over x coordinates equal to -1. And we're gonna do that again just to show you, but it's gonna be like, basically, remember from that other part of the question, we had pi over 4, and we had down here 5 pi over 4. It's gonna be your opposite angles, same reference angle. So the purple one's in the other coordinates, 7 pi over 4 and 3 pi over 4, because as you can see, like, that's x, that's y. Y over x, that's your tangent. These two numbers over each other, one of them's positive, one of them's negative, that'll give you your -1 for your tangent value. Fuck, what did it? Oh, I mean, I didn't say that. So 3 pi over 4, 7 pi over 4. Okay. 3 pi over 4, 7 pi over 4. Those are your inflection points. And I believe that's what is asking for, right? Yeah, find the inflection points and also find the intervals of concavity. So that's what I thought. So if you plug those into like the inflection points, keep in mind, like, it's asking at the original function f, which was your original function. That's just sine x plus cosine x. And then notice the second derivative when I divided out that -1. It's the same as your original function, and that's just like properties of the sine and cosine trig functions. Is like, you take a derivative of it and it's like the opposite one, maybe it's negative, and then you take another derivative and it's like back to what it was before, but it's negative. And that's just like patterns that you see with those. But okay, off topic anyway. So if you evaluated those, f of 3 pi over 4, you'd have sine of 3 pi over 4 plus cosine of 3 pi over 4. And that's okay. Coordinate system, 3 pi over 4, that's over here. That's a negative x value, positive y value. So sine would be root 2 over 2, and then cosine's negative root 2 over 2. That's 0. Just throwing it in to show, since the functions are technically pretty much the same. So that's one inflection point, and then your other inflection point is going to be 7 pi over 4, 0. And I'm going to save you the time of me throwing that into the original function because it's going to be the same thing. Coordinate system, that points over here. You're going to have a positive x and a negative y. So it would literally be the same thing as this, but the negative signs on the x, negative signs on the y coordinate, and positive signs on the x. But since they're the same, then same value, but negative, it's 0. So that's your first inflection point. There's your second inflection point. Now you're gonna want your intervals of concavity, and that is where you're actually looking at the second derivative. So, but I mean, I did solve the second derivative by just dividing out the -1, and then you're back with sine x plus cosine x, which is your original function. So it like, yes, you're looking at your second derivative, but in this case, you may as well be looking at the original function because they are equal if you divide out that -1, which is you're fully allowed to do because you're setting it equal to 0. So okay, 3 pi over 4 and 7 pi over 4. So those are both valid in your interval from 0 to 2 pi, which means that you're going to need to test something in between 0 and 3 pi over 4. A good candidate for that would be pi over 2. That'd be like the nicest numbers you could work with, because that's just going to be like the positive y-axis on your unit circle. And then you're going to need to test something between 3 pi over 4 and 7 pi over 4, which I would choose pi. That's between those two values, and it's going to be the nicest thing you could work with. You could choose 3 pi over 2. That's your negative y axis, but pi's easier. Well, it depends how well you know your circle. Choose whatever. And then you're going to want something between 7 pi over 4 and 2 pi. And that let's see. Yeah, between 0 and 3 pi over 4, something between 3 pi over 4 and 7 pi over 4, and then something between 7 pi over 4 and what do you call it, and 2 pi. So 2 pi, just do 2 pi minus pi over 6, and that's like 12 pi over 6 minus pi over 6, 11 pi over 6. So that's what I would test. That one's going to be your least clean angle. But if you have your unit circle, that's just going to be, so this is pi over 6, the first one, and then the same thing reflected under this way. That's your negative pi over 6 or your 11 pi over 6 reference angle. So that's not too bad. So now let's just check second derivative at pi over 2. And then sine of pi over 2, that's your y coordinate. And again, if we were looking at the unit circle, pi over 2 reference angle is positive y-axis. So y coordinate 1, sine of pi over 2 1, cosine of pi over 2 is 0. So that's going to be 1. That's positive. So that corresponds to concave up. Concave up is if it's greater than 0. Concave down is if it's less than 0. So yeah. So that corresponds to concave up. And that was your interval between 0 and 3 pi over 4. So between 0 and 3 pi over 4, concave up. Next test. Second derivative at pi. Sine of pi, that if you're looking at your coordinate system, your unit circle, pi is right over there, negative x-axis. So sine, your y value, sine of pi, 0. Your x coordinate, cosine, that's -1. So that's -1, it's negative. If you have a negative at your second derivative test, is concave down. So then that lets you know that between 3 pi over 4 and what was our second one? 7 pi over 4 was the second inflection point. It's concave down between 3 pi over 4 and 7 pi over 4. And then lastly, you're going to have to test 11 pi over 6. And we'll just grab our x and y coordinates from that real quick from the unit circle. Come on. Focus. There we go. So, yeah, you can see 11 pi over 6 right here. You got x coordinate √3 over 2. Y coordinate -1/2. So cosine is √3 over 2. Sine is -1/2. So sine is -1/2. -1/2 and then √3 over 2. Come on. So sine is first. It's sine x plus cosine x. -1/2 plus √3 over 2. Square root of 3 is greater than 1, so it's going to come out to positive. And that corresponds to concave up. Between on the interval 7 pi over 4 to 2 pi. And that makes sense considering cosine and sine's a wave function. You know, you're going to expect it to bounce between concave up and down. So that makes sense. It tracks. Let me just go ahead and copy these pictures, and we'll move somewhere with more space. I know it's getting messy in here. I'll just scroll down. Paste. What? Okay, I'll just move them over here. All right. I believe I answered all parts A through C. So, all right, we're gonna run through the same thing with a little harder of cosine and sine question. All right, a pen ink would be nice. We got cosine squared x and minus 2 sine x on the same interval of 0, x is between 0 and 2 pi, but including them. First thing I'm going to do, once the intervals on which f is increasing or decreasing, that's asking about the slope. You know, slope is the first derivative. That'll tell us everything we want to know. Cosine squared x, that's 2 cosine x times chain rule, negative sine x, and then minus 2 cosine x, and then simplify that a little bit, negative 2 cosine x sine x minus 2 cosine x, and I'm gonna go ahead. Do I want to factor that right now? Pull out a negative 2 cosine x, and then you'll just have sine x minus 1. I guess I'll go ahead and factor that. Find the intervals on which it's increasing and decreasing. So set it equal to 0, and when this is greater than 0, your first derivative greater than 0, increasing. First derivative less than 0, decreasing. So this is gonna be fun. Maybe I did not want to factor that yet. All right, so forget the factoring. set it equal to 0. First thing I'm going to do is divide everything by -2. Uh, -2 cosine x, because I can do that on the other side because there's 0 over there, so it'll just go away. But also both, even though I have this subtraction in the middle, since both terms have a cosine x in common, I can divide it out from that everything. So then you're just left with sine x minus 1 is equal to 0. And if you add that 1 to the other side, you have sine x equals 1. Then you can go ahead and inverse sine of sine x equals inverse sine of 1, which gives you x is equal to inverse sine of 1. You can go ahead and look at your unit circle if you need to, but basically it's just asking, sine's your y coordinate. Where is that equal to 1? So if you go ahead, look at your y coordinates. There's really only one place where you have a y coordinate of 1. Down here it's -1, and that's pi over 2 up here. So that's going to be pi over 2. And yeah, that's going to be your only critical point there, it looks like. Let me see. Let me think about this. Am I missing something? By dividing out that cosine x, am I missing a critical point? I mean, algebraically, I should be allowed to do that. Well, just in case. No. All right. Huh. No, I think I'm cool because, like, if I did more steps in here and, I'm like, okay, -2 cosine x times sine x, and then this is equal to 0. I moved the other 2 cosine x over to the other side, 2 cosine x, and then I divide by -2 cosine x. Then I have sine x is equal to -1. So yeah, I would have been missing a critical point had I not done that. I'm trying to think of another way to solve that. Okay, well, interesting. Interesting. Yeah, I guess if you factored it, I guess, yeah, honestly, the best way to go about this would have been to stick with factoring. Oh, come on. Because factoring, you would have had -2 cosine x, and then sine x equal to -1. So then, you take each term in here because they're multiplied, and you're like, okay, when does sine x minus 1 equal 0, and when does -2 cosine x equal 0? So that's how you're gonna have to do it in order to get all critical points. From that second method where I moved everything over before I divided, I got -1. So Now I'm kind of second guessing if what I did here was legal. Dividing out 2 cosine x. I mean, I think it is. So then you're gonna have that critical point of pi over 2, and then this one, the sine x is equal to -1, following the same logic over here of like inverse sine, whatever, looking at your unit circle. That's giving you a critical point of, well, yeah, it would be negative pi over 2, but if you want to keep it all positive, it's 3 pi over 2. That's just your negative y-axis. Um, but then we're also going to have to go ahead and solve this here. Cosine x, divide that -2. It's still just it's just cosine x equals 0. And cosine x equals 0, that's your x coordinate. That is here and here. And this is pi over 2, and this is 3 pi over 2. If you're going backwards, this is negative pi over 2, negative 3 pi over 2. Anyway, yeah, so no, we have all of our critical points. However you want to do it, yeah, so either method would have worked. I guess is what I'm trying to say here. I had to think about that for a second. I didn't see it until I solved this -2 cosine x, because that just gives you like, okay, well, cosine x equals 0 at 2 points on the unit circle, up here and up here. Your x coordinate is 0, which is pi over 2 and 3 pi over 2. But we already got that just from this over here. This sine x minus 1 equals 0, and then also from this right here, where we moved everything over and then divided. That also gave us sine x equals -1, which was our other critical point. But then solving just this -2 cosine x, that gave us both critical points at the same time. So whatevers. However you want to do it, you have 2 critical points. That's pi over 2 and 3 pi over 2. So you want to find where it's increasing and decreasing. Then you'll take your original function. That's cosine squared x minus 2 sine x. And go ahead and plug in your critical points. So if you did f of pi over 2, cosine of pi over 2 is 0 squared, minus 2 times sine of pi over 2, which is 1. It's -2. Yeah, you're looking for intervals. So oops, wait. All right, yeah. Yeah. Forget that. Okay, so our critical points were pi over 2 and 3 pi over 2, and then our interval was 0 to 2 pi. So and that's including 0 and 2 pi. You're gonna want to test something between 0 and your first critical point of pi over 2. We're gonna go ahead and pick something in there. I'll say pi over 4, because it's smack in the middle of those. And then you gotta test something between 3 pi over 2 and 2 pi. I don't know, just subtract pi over 4 from 2 pi and use something smack in the middle again. 7 pi over 4. It's a similar reference angle, just the other direction. All right, my bad. Cosine squared of pi over 4's root 2 over 2 squared, minus 2 sine x. That's also root 2 over 2, because that's the pi over 4 and 7 pi over 4. That's where the sine and the cosine coordinates are equal. And since pi over 4 is in quadrant 1, they're both positive. So that cancels. root 2 over 2 squared. That's just 2 over 4, right? 2 over 4. Yeah. 2 over 4 minus square root 2, I believe. Which is, this is just 1/2 minus root 2, which root 2 is greater than 1. So you're coming out negative here. So decreasing on the interval, that was 0 to pi over 2. Yeah. And then test your other critical point, or like, I guess test between your other critical point at 7 pi over 4. At 7 pi over 4, it's the same coordinates as pi over 4. Pi over 4 was here, except for it's down here. So your x is still positive, but your y is negative. So sine's negative, cosine's positive. So that's just root 2 over 2 squared minus 2 times negative root 2 over 2. Yeah, because your y is negative at that reference angle. It's in the fourth quadrant. So that just gives you 1/2 again, plus root 2. So that's positive. And then you'll be increasing on pi over 2. Wait. Yeah, increasing. Wait. Okay. That's increasing on 3 pi over 2 to 2 pi, and I'm a silly goose because I forgot to pick a reference angle in between in between pi over 2 and 3 pi over 2. So I got one between 0 and pi over 2, and I got one between 3 pi over 2 and 2 pi. But we need something between pi over 2 and 3 pi over 2, right? So I'm just going to go ahead and say pi. That one's easy. Easy choice. Easy choice. So f evaluated at pi. Cosine of pi is -1, but then that's squared. Cosine of pi is -1 squared. -2 times sine of pi, which is 0. Sine of pi is 0. That's over here. That's that reference angle at pi. So that is just 1. I'm pretty sure, I don't have a calculator, but I'm pretty sure you just take that and square it. Yeah. No. Yeah, I'm tripping. All right, 1. So that's positive 2, and it's going to be increasing on what was that? Pi over 2 to 3 pi over 2. That's increasing. All right. Somewhat painful, but there we got that there. Find the local maximum and minimum values of f. Of f. Okay. Find local and maximum minimum values of f. So we're going to take our critical points and our endpoints. Critical points were 3 pi over 2. Let's see, pi over 2. And then those were our only two critical points, but we're going to need our endpoints, so 0 and 2 pi. And we're going to plug those into our original function, which is cosine squared x minus 2 sine x. So at 0, cosine of 0 is 1. So we'll have 1 squared minus sine of 0 is 0. So that's just 1. At pi over 2, positive y-axis, cosine 0. So 0 squared minus 2 times 1, -2. 3 pi over 2. 3 pi over 2, that's negative y-axis again on the unit circle right down here. 3 pi over 2 cosine 0 minus 2 times sine of 3 pi over 2 is negative 1. So that's positive 2. 2 pi, that's just the same as 0 again. That's 1 squared minus 0 is equal to 1. So then you'll say, okay, I got an absolute and a local min at pi over 2, negative 2. And then you'll have a absolute and local max at 3 pi over 2, 2. And then maybe I should use a different color for that real quick. 2 seconds. And then you'll say local maxes, maximums, maxes, however you want to spell it, at 0, 1 and 2 pi 1. Yeah. Okay. Part C, we're almost done, I promise. Oh, find the intervals of concavity and the inflection points. Okay, so you're gonna take your second derivative. I think I'll pull my first derivative up here, make it a little easier. Copy. Okay, so we want the inflection points and the intervals of concavity. First thing you gotta do is take your second derivative. So cosine x times sine x. I'll leave this 2 out front for a second and just focus on this part. 2 times let's see, product rule. Cosine x times derivative negative cosine x plus negative sine x times negative sine x. And this is all in here. So then 2 negative cosine squared x, those negatives cancel, plus sine squared x. So then you just have 2 sine squared x minus 2 cosine squared x. All right, cool. Inflection points of and intervals of concavity. Set that equal to 0. First thing I'm gonna do, you know what, we'll work through the steps on this, and won't shortcut you. Add that 2 cosine squared x to both sides. So then you can divide both sides by 2 cosine squared x. Twos are gonna cancel. You're gonna be left with sine squared x over cosine squared x equal to 1. Sine x over cosine x is tangent, right? So sine squared x over cosine squared x is going to be equal to tangent squared x, I believe. So, I just blanked for a second. Alright, inflection points. So, inflection points where tangent squared x is equal to 1. Okay. So, we could, I guess, I mean, this one's simple enough. You could do it without, you can see it without this, but I'll do it anyway. So square root of 1 plus or minus 1 equal to tangent x. So when is tangent x equal to plus or minus 1? If we look at our unit circle, we know tangent is y over x or sine over cosine. So right here, it's going to be equal to 1. Down here, it's going to be equal to 1. And we'll use a different color. Here is going to be negative 1, and here it's going to be negative 1. So we got pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. What did I say? Pi over 4, 3 pi over 4, 7 pi over 5 pi over 4, and 7 pi over 4. Those are our candidates for inflection points. No, actually, those are our inflection points. So what was the? Let me look real quick, because there's something about like it could not be an inflection point. Oh, it's just like if it doesn't change from positive to negative, like there's no sign change, but on either side of the inflection point, then it's not really an inflection point. It could just be like a point where the derivative is 0 or something, or there's like a discontinuity or like a sharp curve in the graph. Okay. Well, let's get on with it. Let's get on with it. So what does it want? Intervals of concavity and the inflection points. Alright, so to verify if these are inflection points, we're gonna have to find the intervals of concavity first. And that's gonna be plugging these into the second derivative, but we're not exactly plugging them in. So we this is on the interval 0 to 2 pi. So first thing, we need something between 0 and pi over 4. So let's just say pi over 6, because what else are we gonna choose? Then we need something between pi over 4 and 3 pi over 4, and I'm gonna choose pi over 2 because that's a nice angle. Then we need something between 3 pi over 4 and 5 pi over 4. I'm gonna choose pi because I like that too. And we're gonna need something between 5 pi over 4 and 7 pi over 4. And I'm gonna say 3 pi over 2 because yeah, that angle, I like that one. Then we need something between 7 pi over 4 and 2 pi, and I'm just gonna use 11 pi over 6 because there's nothing else nice in our options right there. So yeah, let's go ahead and test this with the quicks. So we're plugging these pi over 6, pi over 2, 3 pi over 2, pi, 11 pi over 6. We're plugging those into the second derivative here. And yeah, honestly, you could probably divide out that 2 and make it a little nicer, but we're good. We'll say if you evaluate it at pi over 4. No, we're not doing pi over 4. We're doing pi over 6. Pi over 6, cosines root 3 over 2, sines 1/2. So, oh, come on, load. Okay, so visually, just looking, I said Cosine was root 3 over 2. Sine's 1/2. Dang. So sine is 1/2. Square that. 1/4 times 2. 1/2 minus 2 times root 3 over 2 squared. 1/2 minus those 2's cancel, so you 3 over 2. This is negative. This is negative. My phone's blowing up. That's negative. Right? Right? Yeah. So, just as a reminder, if your second derivative is negative, corresponds to concave down, and positive, you have concave up. So that's gonna be concave down there. So we'll make a little list over here. Concave down, on the interval. That was for 0 to pi over 4. But we're gonna keep this list open. We'll use a little u, that means union, which means we're probably gonna have more concave down intervals in this in this set of domains. All right, let's get on with it. Let's get on. What are we testing? All right, we did pi over 6. Pi over 2. That's nice. All right, pi over 2. I could do this in my head. Sine of pi over 2 is 1 squared. 1 times 2. 2 minus that's 0. Cosine of pi over 2 is 0. So we're left with 2 there. That's positive. So we're gonna add that to our concave up interval. That was pi over 4 to 3 pi over 4. All right. And maybe we'll move that right here, because it's going to be in union most likely with some more domains. We got a couple more to test here, and then we're done. So second derivative at pi, this can be our next one. That's also easy. Sine of pi is 0 squared times 2, 0, minus 2 times cosine of pi squared. That's cosine pi is -1 squared. 1 times -2. That's -2. All right, so another negative. Joining the concave down set. What interval was that? That was 3 pi over 4 to 5 pi over 4. All right, see? All right, we're getting somewhere here. Next one, 3 pi over 2. All right. So that's easy. I could do that in my head too. Plugging that into your second derivative. Sine of 3 pi over 2 is -1 squared. 1 times 2, 2 minus that term will be 0. So what did I say? That's -1 squared. 1 times 2. That's 2. So that's positive. That's gonna be in the concave upset, and that'll be 5 pi over 4 to 7 pi over 4. And logically, like, that makes sense. You got wave functions, it's alternating, like, yeah, it makes sense. And the last thing we gotta test, 1, 2, 3, 4, 5. Yeah, last test, 11 pi over 6. I'm gonna have to look at the unit circle for this. 11 pi over 6 is right here. That's your x, or your cosine. That's your y, your sine. Y is negative, cosine is positive. Root 3 over 2 and -1/2. Yeah, so let's go ahead and do that. Sine is negative 1/2, so we got negative 1/2 squared times 2 minus 2 times root 3 over 2 squared. That's going to be 1/4 times 2 is 1/2. That's 1/2 minus, it's going to be 3 over 2 minus 3 over 2. Yeah. So that's gonna be negative. So that's joining your concave downs. That's joining concave down. That's 7 pi over 4 to 2 pi. So maybe like move this over a little bit. Union 7 pi over 4 to 2 pi. Yeah. So these are your concave down interval right here. And this is your concave up interval. Yeah, so find the intervals of concavity and the inflection points. So I'm gonna make this quick and easy on you. Since it was alternating, like as you go in order of these reference angles, as you went in order, it kept switching between concave down and concave up. So every single one of these is going to be an inflection point. That's what that means. If like two intervals side by side were both concave down, then it's like you wouldn't need the union. You would just like say it was these ones. Then instead of union between those two pairs, you would just say it's from 3 pi over 4 to 2 pi. But since you have those unions, that implies that the interval's broken up. It's like alternating concave down and concave up. So then if you want to state your inflection points, if you want to state the actual values, like ordered pairs of your inflection points, then you take those green numbers here, like the basically the critical numbers that we solved in the second derivative there. You take those, right? You take these and you plug those in to the original function. So you just do like, come on, f of pi over 4 equals, I don't know, 7. It's not 7, but that's how you do it. And then you'll say you have an inflection point here at this ordered pair, and then do the same thing with the other 3 options. So just plug all those into your original function and get your output, your y value, and then state your inflection points, and then you're done. Because you had to verify that your concave up and your concave down stuff before you could say that they're for sure inflection points. Because they were just candidates for inflection points. You have to make sure that at those points it's actually changing from concave up to concave down to say it's an inflection point, which we did. They alternate all the way through. There's no critical numbers there that are not inflection points. So just go ahead, plug those into your original function, work it out. I believe in you. You got this. And then state those. And this was a little bit of a longer video, so but hopefully it helped pretty good.